Okay, so I'm going to take this opportunity to talk about my newest fascination, my newest really interesting area I've been learning about called reinforcement learning. And this is basically the concept, the mathematical sort of framework of reinforcement learning had been around for several decades. But what's happening now is that with the application of increased computational power and deep learning techniques, combining them together into deep reinforcement learning, it's becoming the type of behavior that you can generate. And if you're kind of training an agent to solve some problem or do some kind of, there's many different behaviors that you can get out. It's very interesting to me because you can generate these, really often you can generate these very lifelike behaviors, which were not really that possible to achieve in the past. My area of research I'm still in my PhD program, has focused a lot on agent-based modeling, which is basically, if you're familiar with this, it's like you are giving a set of rules. You are programming, it's like with my work with ants and kind of simulating ant behavior and ant movement, you give the individuals, you hand program these rules about how the individuals will act, how they will move, and how they will interact with each other. And you just define it in the code, what the rules they're going to use to take their actions. You know, what will happen if they encounter another individual, if they encounter a certain situation, and like I have them kind of just move across the space. And so agent-based modeling, the field of agent-based modeling is kind of like that, where you are, oh, this area looks really interesting. I'm coming up on over here. And how that relates to what I'm particularly got really interested in now is the idea of training AIs, training these reinforcement learning agents in a simulated 3D environment, or in some kind of environment, and then they can kind of interact with that environment and learn to play these games or behave cooperatively or act, you know, and they can become so good sometimes at playing these games that they go above human level performance on trying to play that game. So it's very interesting. It represents to me like a fundamentally new way to find solutions to problems and even to like access knowledge. It's like in a way, it's like if you have trained an agent on some kind of task that and they become so good, like in the example of AlphaGo, if they become so good that they are beyond, you know, they have a superhuman level intelligence or performance on that task, then it's in a sense, it's like a way of learning. You can learn from that individual. You can gain new knowledge just because that agent has sort of mastered it to a higher level than any person ever could. So you can kind of use that. That's like a way of just gaining some information and some knowledge in a way. You know, you can observe what that trained agent does. I wouldn't go back to the point. So basically, the way that agent-based modeling kind of ties into this burgeoning area of research is like, apparently in the past, if you're playing like a video game, and the game is the aspect of playing a game is just one sub area of the whole field, but if you were playing a game like a Mario Party, or you're playing against some computer, like they called it CPU, you know, in the game you're playing against the computer, that apparently up till very recently was that was they call it hard-coded or hand-coded rules, just like what you would do in agent-based modeling. Like you are going to define how you want that agent to behave. by giving them rules that we as humans come up with. And that's what you're also doing in agent-based modeling. I'm gonna take a look at this lichen real quick. This is another target for me is on the trip is to, or in this other video, I want to kind of look more at these like different lichen morphologies in the ecotones as we go up, as we go across the landscape. The difference now, or what's beginning to emerge, is that you can, instead of hand coding these rules by which the computer agent is going to act, you can begin to grow. You train them, or you basically you train some kind of deep learning architecture, some kind of neural network that it's essentially like you're allowing them to discover the rules of the game on their own, and you don't have to explicitly tell them anything to do. It's like kind of like, to me it seems like I would call it like hands-off parenting. You could just kind of release them into the world and let them figure out what kind of behaviors will be rewarded or penalized. So that's the idea. Basically, this area of research is growing really fast, and it's just very interesting that it allows you to basically you can grow an agent that can have these very lifelike features that can solve these problems without really having to know yourself how to directly explain that behavior. Tell them, directly what that behavior should be. And I think that it definitely took me too long to realize that in agent-based modeling, I feel like it was not really, it just seems to me like this, what's happening now with being able to train these agents, that it's sort of like the next step, the most logical next step. It's like a much better way to go about it. And the reason is because you can't really, one of the main things I've learned in my studies is like, you cannot really design, as humans it's very difficult to design complexity in the sense of complex systems, like it's like, you think about the complexity of a system. One of my favorite examples is like the cell, which I don't know if I've talked about that before, but the cell, with all of it's so many different moving parts. The molecules are just bouncing around, and each of them has a particular, it's kind of evolved to have a particular function, and it has occupies a certain function inside the metabolic network. If you look up, there's these diagrams of the metabolism network, and you can see all these huge number of components that all are sort of interacting. And sometimes the basis for a genetic disease is if your body is miscoding one of these proteins, or one of these components is not quite right, it can cause a havoc on when you go up to the large scale, the scale of the systemic level of the organism. So how did it get like that? It's like it evolved basically to have all these pieces perfectly working harmoniously together. Just basically a lot of trial and error, right? So to make a system, I mean, that's a extremely complex system. I kind of like that because it's similar to what I work with, which is a bunch of particles that are kind of interacting with each other. And through my research, I found that you try to design a system like that exhibits a kind of complexity. Like a cell, does all of its functions, like mitosis and apoptosis and all that stuff on its own. All those global level phenomena that happen are emergent from all the interactions between all those molecular components. And as humans, it's extremely difficult to try to design that. It's like you basically can't think of everything that is necessary it's just basically hard to create that kind of emergence and create something that can have those emergent features at the large scale. So what I've learned over time is that because basically your only real hope is to try to grow a system like that, to try to mimic what evolution did by sort of, in terms of mathematically, it's like kind of you're optimizing something. You're trying to solve some kind of optimization problem. Like if you're familiar with the concept of genetic algorithms, you can grow, you can evolve sort of agent to behavior in that way as well. And over a series of generations and trying to selecting for individuals which were able to complete the task the best. Like there's an example where like there's a really well-known result where they trained these individuals to like run, and who could, what type of locomotion or what type of shape would allow them to, run these virtual robots to travel the fastest across the surface. So that I really like too. It's like, and that's a very parallel thing is happening with reinforcement learning now, but the point is that to get that kind of complex behavior like that, it's like you're better off trying to optimize for it as opposed to design it yourself. And that's why I'm trying to go more and more towards this area now with reinforcement learning, is because it's definitely feels like a better way to basically, it's kind of like almost like you're creating life, or creating it's almost like you're modeling behavior in a better way.